This is a video demonstrating time constants. I've set up a circuit that is a square wave driving a resistor and a capacitor in series, and I've set up the oscilloscope to see the voltage across the capacitor as the rise time and fall time depends on the time constant tau. Here's the circuit right here. It's kind of ugly. This is a resistor box. I've chosen 10 kiloohms and a capacitance of 10 nanofarads. Right here, the capacitance is actually 10.16 nanofarads, but very close to 10 to the minus 8 farads. Okay, now the time constant is RC, and for 10 to the fourth ohms and 10 to the minus 8 farads, we get 100 microseconds as the time constant. So I have the waveform generator. This is 10,000 hertz times 0.1. I have it set here to 1 kilohertz. I'm going to prove to you that it's 1 kilohertz. You can see that one period is 1,000 microseconds. So that's 1 millisecond, which is the inverse of 1 kilohertz. So we are good for the frequency. I also want to show you that the voltage that I have it set to is exactly 1 volt, well, very close to 1 volt. And the reason for doing that is I want to demonstrate the time constants as a percentage of the voltage, and it makes it easy if it's 1 volt. So say one time constant where it rises to 63% will be 0.63 volts on here. So let's start doing this. Let's see where we're at. Now, the time constant, again, RC for 10 kiloohms and 10 nanofarads is 100 microseconds. So we go up here and we'll change it to delta T and we'll dial in 100 microseconds. So this is an old school analog oscilloscope with some digital features. Now, it's not very good, but we're going to want to zero in on this point right here. Now, let's see what the voltage is at that point. I think I'm going to try to leave my pointer right there. And let's go to delta V and drop this to 63%. And 63% is right there, yeah. So there you go. 63% is, in fact, one time constant, 100 microseconds. Let's repeat that for 2 time constants. If we go out a time constant, or a time equal to 2 time constants, look here. After 2 time constants, it will have risen to 86.5% of its maximum value. I think we can change this here first to, oh, I wish I hadn't done that, to 200 microseconds. Let's go out to 200 microseconds. And now let's look at the voltage and go up to 86.5, 86.5 or so. Things aren't that accurate, but I got that. So let's go back. This is the time right there of 2 time constants, and it should be, the line should go right through that, and it does. So that's exactly 2 time constants of time, and as I showed just a second ago, exactly a rise time of 86.5%. And just for fun, we're going to do it one more time. Over here, 3 time constants is 95%. As if you need convincing, let's go up to 90.95 volts, which is 95%. And I'll place my pointer, my high-tech pointer right there. And we will go out 300 microseconds. Whoops, delta T. We'll go out 300 microseconds. And it's pretty close to exactly where it needs to be. Right there. Yep. So those are time constants for tau, 2 tau, and 3 tau. And the fall time does exactly the same thing. It falls to 37%, and then, 37%, and then 14%, and then 5% after 1, 2, and 3 time constants. I could do that and show you, but you can see that it's symmetric.